Thank you, Richie. So to start off our announcements, as many of you may have heard, Brother Curtis, the teacher of the 112 class, had a stroke a few weeks ago, and so he was not able to teach that anymore. And so a substitute for the construction management major, Dr. Young, Dr. Miller, not the Dr. Miller, teaches this class. Died in a car accident, and so there will be a fundraiser for his family in the next 2 days, and there will be more on that on the blog. Ways to donate to that if you feel so inclined. So we're excited to hear about that. The IT highway cleanup will be happening March 24th. So this is a good opportunity to get service points as the semester is coming to a close. So signing on the docs and the blog. Also, next Monday, March 26th, the Red Cross will be here for the blood drive. So it's a good way to get service point for donating blood, and it also helps to save lives. And as we have the other opportunities, we'd like to sign up for that as on our website. Choose to Give is a great way to give back to the university and to the funds, which help with scholarships and things like that. Many of you might have been recipients of scholarships, and this is a great way to give back. It doesn't need to be a lot, small contributions add up. And so we also need volunteers to help man for that in the upcoming week. For the Rocky Mountain Conference, the people who are attending, I really need your attention for this. We are just 2 weeks away from the conference, and so there's a lot of things that we need to get finished wrapping up. And so Jolene sent out an email yesterday with a lot of information. There are 2 things that we need you to do today. And so here on the Google sheet that is on there, a lot of you already filled out your phone number, email, and whatnot, but we need you to put in your request for the food banquet. And so there's just a little drop down there, you can choose from that. We need all of your food preferences and shirt sizes by today, or I'll be making those up for you. So please get that done by today if you're attending RMC. Also be sure to pay your fee for travel and hotel if you're going. And if you have food allergies, you can put that in as well. And more details will be coming in the next few days with more specifics on that. And so if there are people on there who have not filled in their information, but you are friends with them or know them, please get a hold of them and ask them to do that for us. Tonight at 7 o'clock in the Clyde building, there will be a March Madness party where we will be watching March Madness. Please be sure to sign up on the Google sheet sent out by Kim before 1 o'clock today, or you will not get pizza because we need to order pizza for everyone. We want to make sure that there's enough. There will be a presentation by Dr. David Noyce tonight in the Clyde building between 5 to 6 and 5:30. So they'll be giving a transportation presentation if you're interested in that. For our Station field trip, this will be an exciting opportunity to go visit the station and to see how it works and what's going on. So that's March 30th. As always, the sign-up is on the Google Doc. And just a helpful way to get all of these activities on your Google Calendar, you can add the Google Calendar of activities for BYUAS. You can follow the instructions here. Today there will be a meet and greet with David Friedman today from 1 to 2 p.m. in the Crabtree. So if you're interested in meeting with him and talking with him, please feel free to come to that. And now, without further ado, we will have Dr. Richards to introduce our speaker for the day.
All right, it's a pleasure to introduce our speaker today. David Friedman is a senior principal and emeritus president, CEO, and board chair of Forel Elselser Engineers Incorporated. He has over 40 years of professional practice in structural and earthquake engineering. David's strength is a holistic approach to a project's planning, design, and construction, and the collaborative integration of creative structural solutions with architects, engineers, and builders. With a specialty in designated historic structures, David has creatively solved numerous engineering challenges. Principal examples of his solutions include the base isolation retrofits for both the San Francisco City Hall and Asian Art Museum, the adaptive reuse and retrofit for the San Francisco Conservatory of Music, and the seismic safety corrections and remodel of UC Berkeley's California Memorial Stadium. David knows firsthand that the practicing structural engineer today must have a broad understanding of not just structural engineering, but must be knowledgeable about architecture, MEP systems, construction delivery methodologies, and the construction process. David is devoted to worldwide seismic risk reduction and is the president of the Earthquake Engineering Research Institute and the current director of Build Change. He is also deeply involved in many other civic, philanthropic, and not-for-profit boards, including the San Francisco Foundation, the San Francisco Bay Area Planning and Urban Research Association, UC Berkeley Foundation, Jewish Senior Living Group, Fault Line Foundation, and the United States Resiliency Council. David and his family generously endowed the Friedman Family Visiting Professionals Program in association with EERI, which has created opportunities like this one today for many universities across the world. Please join me in welcoming David Friedman.
Jeremy? All right. All right, you know a little bit about me. Actually, you know way too much about me. So I want to know a little something about you all. How many of you are undergraduates? Graduates? Professors? How many are structural oriented? Geotechnical? Wastewater? Okay, well, thank you. It's nice to be here. I have way too many slides. I'm going to go really quickly. I'm going to really tell you a story about my career and how it was deeply influenced by a number of different things, but mainly earthquakes. And so I'm going to start with an unpaid advertisement for EERI. I've had a 25-year involvement with EERI. It is a global earthquake engineering institute. It's a non-profit membership organization. I would highly recommend, even if structural and earthquakes is not your thing, there's something about this organization that is really quite extraordinary in its ability to mix its mission and its vision across interdisciplinary lines, including social science, around disaster, around resilience. So I highly recommend not only being involved in the student chapter, being involved in the regional chapter, and then once you're in practice, become a member. And there are quite a few benefits to being a member and inducements to going from a student member to a practicing member. We have an extraordinary program in seismic safety in schools. We have a new, Learning from Earthquake is really our flagship program, and it has been expanded into doing an on-site learning where students and young professionals get to travel to post-earthquake sites. It could be a year or two after an earthquake, but there's quite a bit of learning that can still be done from that travel study program. So there are regional chapters. I understand you have a very strong Utah chapter. I'm not sure exactly where it's located, but it would be great for you to get involved in that. First year of membership is free, so I just highly recommend you get involved. I highly recommend you get involved in all sorts of professional associations, because there's nothing that gives you that kind of opportunity for leadership development, for exposure, and for the people that you will meet. That's how it charted my course. So I've added a new slide to a series of slides in my presentation. This is my career timeline. I've had 3 jobs in my entire career. A 2-year job, a 3-year job, which I liked much better, that made me decide I really liked consulting engineering. And then a 38-year job that is ongoing with Farrell Elsesser Engineers. as my wife put it on my 35th anniversary there, was either you have a lot of stamina or you have no imagination. So as I said, earthquakes have marked my career. So I added that to the timeline. It is remarkable how some of these earthquakes have either impacted me directly, impacted a project I worked on, or was a major influence in terms of code changes. There's a reason we chase earthquakes around the world. And chasing them with an interdisciplinary team is always the most interesting part of that. So I was not alive in 1906, but the great earthquake in San Francisco really was important, because that's a photograph of the old San Francisco City Hall that was damaged in the 1906 earthquake. And later on, I would spend 10 years of my career, which I will tell you about, in the renovation and retrofit of the new San Francisco City Hall. San Fernando earthquake had a major impact on what we now require for the design of hospital buildings. That was a hospital. We now design hospitals throughout the country, but particularly in California, for much higher seismic standards. 1989, there was a little earthquake in San Francisco. And the bane of my existence now is people who say, my building made it through the big earthquake. 1906? 1906? No, 1989. It was a tiny earthquake. And it really did not attest to things at all. Northridge, 1994, was a really good example of about the code minimum. The code minimum with earthquakes doesn't always work. This was a code-complying building, except for one thing. It did not adhere to the provisions about diaphragm aspect ratio, so that just rolled over because of displacement. 1995, I was on the post-earthquake reconnaissance trip to Kobe, Japan. For me, that was a huge eye-opener, because what it taught me, this was an Embarcadero type freeway, viaduct structure, brute force approach to seismic design. The larger you make it, the heavier it is, the more seismic force it will attract. Banda Aceh opened our eyes about tsunamis. Wenchuan, China, this was very important in my career because I met someone influential in my life, Elizabeth Hausler, who started a nonprofit called Build Change that does seismically safe housing in the developing world. So now at the end of my career, I can now devote time to being on the board of organizations like this. Haiti just broke my heart. Being on that post-earthquake reconnaissance team, that country was destroyed by an earthquake and barely is recovering now. Christchurch was a modern earthquake with great building codes, great construction, and that central business district today is still destroyed by that earthquake. Tohoku, Japan, another tsunami. Heard about the power plant but what was important about this earthquake is not only do we measure Richter magnitude, the duration of ground motion means a lot in terms of a building's response. The Tohoku, Japan earthquake lasted 2.5 minutes. One of them, that strong ground motion. So it was really interesting. So, structural engineering. Here's my favorite definition of structural engineering. Structural engineering is the art of molding materials we do not entirely understand into shapes we cannot precisely analyze, so as to withstand forces we cannot really assess, in such a way that the community at large has no reason to suspect the extent of it. Unfortunately, it's entirely true. There's a lot we can do, but at some point you have to use a lot of judgment in what you're doing. So I'm going to pontificate for a few minutes about what I've learned and some lessons learned. The building code. We change the building code as we learn things over time. The building code, when I started practicing with respect to earthquake, was about 11 pages. Today, it's 3/4 of an inch. I'm not sure it's all that much better. certainly is more detailed. But we've learned a lot of things from chasing earthquakes around the world. But the code is still a life safety code. What does that mean? It means that you design the building to safely get out. It says nothing about your ability to get back in. In fact, it can be a complete economic loss. That is the basis of our building code. And I've come to believe that that is really not sufficient when we know we can do better. The codes are based upon regular buildings, not really based for irregular buildings like the one shown on the right. Again, the building code is based upon life safety. A colleague of mine made this diagram of Joe's bar, because everyone can relate to a bar. So on the right side of the slide are buildings that will be highly damaged in an earthquake. Those are actually the code compliant buildings. What we're trying to do, what I'm trying to do these days is advocate for lower levels of damage, operational buildings, buildings that can be repaired in short time with a short amount of repair. That's what I call seismically sustainable buildings. And there is a whole movement afoot to do more in the way of seismic resilience. Architects that you work for don't like doing regular buildings. They like doing buildings like this, or this. This is actually not a building after an earthquake. A large part of what you do in practice is the documentation. You're putting together a set of drawings, plans, specifications, details. Today, in my day starting, I used to do hand-done drawings in pencil. Today, it's all done by them, by AutoCAD. I don't even know how to draw a straight line in AutoCAD, but everyone today does seem to know how to do that. But the importance of documents is critical because a contractor is going to try and pick it apart. They're going to try and find the mistakes, and they're going to hammer the client because of that, and then the client's not so happy with you. So quality control of your documents is a very important thing. I was taught early on that during the course of construction, the design engineer stays out. That's what the contractors are responsible for. It's called means and methods of construction. But so many of my early projects were retrofit projects where I cared a lot because we were actually destabilizing the building until we were able to make it stronger. So a lot of our work does tend to pay attention to the stability during construction. Construction administration is an important part. After you design the building, put the drawing together the best you possibly can, you turn it over to a contractor, you review shop drawings, which is your chance to look at the vendor drawings to make sure that it's being interpreted well. But contractors still make mistakes. Like, you think those two joists were supposed to align? You think that column was supposed to be plumb? You think this followed the typical detail of spacing and penetrations through the slab? No, it's kind of just caused a shear zipper through that. So these kinds of things are dramatic, but this is why an engineer goes to the field periodically, not to provide special inspection, but to be able to make sure the construction is happening in the way it was designed. As I mentioned, sustainability has become a new buzzword, but they kind of left out seismic sustainability, which is why I put down at the bottom, there is this U.S. Resilience Council, a rating system for seismic performance, kind of like a REED rating system. You probably have heard of that. But this is trying to draw the public's attention to the safety of the buildings we live in, we work in, and pray in. Communication is a really important part of the practice, written and oral. In fact, most engineers get the bad rap and the stereotype that they don't know how to write. And to some degree it's true. But what you have to do, it is possible to write well and to communicate well. What's hard for an engineer, though, is you're communicating technical stuff to a lay audience. And you have to understand that and appreciate that, and sometimes intentionally dumb it down. And we've actually found ways of making movies, of diagramming things to help illustrate what it is we're trying to advance. So I'm going to talk to you about a couple of my projects. So on my timeline, I superimposed some of my projects. And the two highlighted, San Francisco City Hall and Memorial Stadium at University of California, Berkeley. You'll notice the 1 decade time span of those projects. That is not typical. There were reasons behind that. They were unusual projects. They were one-of-a-kind projects. And so there was a lot of scrutiny. And in fact, on the Memorial Stadium project, there was 2 years of litigation to try and stop the project. I decided after spending 2 years with attorneys that I like architects much more than attorneys. So how many of you have ever heard of base isolation? A few. That's good, because I thought I'd do a little primer on what base isolation is. Okay, so base isolators. There's really 2 basic kinds. There's an elastomeric one, the top 2, and what they are layers of rubber, high damping rubber, and steel. Rubber, steel, in layers. Vulcanized together, kind of baked together like a birthday cake, that are vertically very stiff and laterally flexible. The one on the right is another type of elastomeric bearing, but it has a center core plug of lead that adds to the damping characteristics. A third kind is called friction pendulum. Today we use all of these almost interchangeably. The vendors for them, and when we first started, there were only proprietary vendors of each. Now it has opened up to be a much more competitive marketplace. Why do we use base isolation? 2 reasons. One, on the left is a typical fixed base building. Fixed base would be a concrete frame building, a braced steel frame building, a concrete shear wall building, where the base of those walls are really heavily connected to the foundation. On the right is the base isolated building. You can see those red isolators that are yielding, that are stretching. But there is diagrammed the value, one of the values. On the left, the traditional fixed base building is deformed, story by story. That's what causes the damage in the building, the deformation. And Earthquake Engineering 101 is about the being able to absorb and dissipate the energy of the earthquake. The way that the fixed base building is doing it is by cracking in the shear wall, displacement of the steel frame, but that's what's causing the damage. But in the base isolator, most of that energy dissipation is happening in the isolator. And you can see the rest of the building is moving more monotonically, more as a shape. So there's less inter-story deformation and less damage. That's reason number 1. Reason number 2 is what we call the period shift. So in this response spectrum graph, you see most fixed base buildings are in the lime green zone. And you can see that a 5-story building probably has a half a second of fundamental period of vibration. You can see that puts it at the top of the response spectrum. So if you read over to the acceleration, the lateral acceleration, it's over 1.0 G. But in a base isolated building, we soften the period of the building to between 0.2 and between 2 seconds to 3 seconds. And if you read back over to the acceleration, it's like 0.2 G. So we get almost a 500% reduction in the lateral force that we're designing for. During the course of my career, we've been involved in all of these base isolation projects. Most of them retrofit at the beginning. It's a lot easier to do for a new building. The very first building that we did was the city and county building in Salt Lake City. They were the first ones who said, yes, we'll try this. And we also, more recently, did the Utah State Capitol building, which is also base isolated. So I'm going to talk to you about San Francisco City Hall. San Francisco City Hall was rebuilt in 1916. There's another photograph of it after after the 1906 earthquake. It was moved in a site across the Civic Center Plaza. This is essentially what we did. So if you look down at the bottom of the slide, I don't know if you can read it very well, but you can see almost an isolation plane. We created a new floor below which are the isolators. Put in a new foundation, and I'll show you some pictures of that. We still had to do some stiffening of the light ports. It's a very symmetrical building on each side of the dome, the drum. But we put concrete shear walls up through the inside. We also had to stiffen the drum that supports the dome, and then create a transfer mechanism from the dome down to the shear walls. Now, to demonstrate to the clients, I hope this works. So what you're seeing on the left is the fixed base building, on the right is the base isolated building. This is a real-time history earthquake response beam. Look how much the dome is moving on the left, how it's distorting. But under the base isolation, you can see those spring constants mimicking the isolators. And you can see how little the dome is moving.
Do you know, has this been magnified at all?
Absolutely, yeah. For your viewing pleasure. Yes, it has, but it is symbolic of the stresses that the building is undergoing. So it was long after we were under construction that we had the technology and the ability to show this to the client. But this is this kind of in one animation explains the value of this. So now a couple of photographs. So this shows we excavated, we demolished all of the partitions that were there that were all hollow clay tile. You see the reinforcing steel for the new foundations going in around the existing concrete foundations. The concrete columns have been stripped of their concrete encasement. And then that gets ready for this. So on the left, you see an armature of steel. This is all designed by the contractor, but we gave them the loads. This is meant to be a load transfer, to bypass the loads through the columns. And then you can see the cylinders on each side, the 3 cylinders are hydraulic jacks. So we jack this up. Jacking up is a misnomer in that it actually is just trying to relieve the stress in the column so that we could come in and cut the column. And then you can see on the left side, you can see where the isolator has been slid in, and there's a steel cruciform that's on top that's going to be part of the future floor. In some cases, we had multiple, because of column weight and load, we had 2 isolators underneath, and you can see there are some plates around that. We locked the isolators down because until we installed all 468 isolators, it wasn't ready to be released. In fact, we had to do the rest of the stiffening through that. There were 4 or 5 column towers that support the dome, and this took an extraordinary bit of racing to support and do the load transfer there. And then this is a last shot of the new steel floor where you can see the seismic isolation plane below that where the isolators are residing. And then we put steel deck and concrete on top, so we had a nice stiff diaphragm to load all of the isolators more uniformly. As we were finishing up the construction of San Francisco City Hall, we competed for the Asian Art Museum project. It was designed by the same architect and the same engineer, same construction techniques. This was the old city library being converted into a museum, an Asian art museum. And it was essentially the same thing. We were creating a new isolation plane, stiffening parts of the superstructure. But in competing for the job, it was a historic building, and we kept saying we can do the same thing for this building, we can protect the building. And the owner and the architect both turned to us and said, that's very nice. We don't care about the building. We care about our collection. And the only way of preserving the collection and to protect it in an earthquake was to base isolate the building. So it was actually my first lesson on how base isolation and content and non-structural elements are about as much of earthquake engineering as the primary structure. Okay, another 10-year duration project of my career, and that's California Memorial Stadium. It was actually two projects. In the foreground, you might see down in here a kind of crescent-shaped building that became the student-athlete high-performance building. So all of the program areas within the stadium could be decanted out so we could do the retrofit of the stadium. The stadium was built in 1922. It was carved out of a hillside, so one half of the stadium is just a slab on grade, so we had no concerns about that. I love seeing the mules doing the excavating in this. The stadium was built in 9 months for the cost of $1 million back in 1922. And I said that we spent 10 years in design and construction. This shows some of the scaffolding and shoring for the new West Bowl. As you probably know, the Bay Area is ringed by earthquake faults. There's a line, an arrow that points to the Hayward Fault. That arrow is pointing exactly to California Memorial Stadium. The faults are all right lateral faults, meaning they're moving more horizontally than they are vertically. But we knew from the beginning that this building sat right over the top of the fault. And here's it for geotechnical engineers in the room. This really explains, and in light green you can see this shutter ridge that is geologically over time what has created this. You also see Strawberry Creek that runs, and that's also an indication of how much creep has happened in the fault. The creep in the stadium was pretty interesting to us to track what had happened to the stadium over time. We also, because of the litigation tried to stop the project, particularly the student-athlete building, that crescent-shaped yellow building. Because there was a law on the books in California that you cannot build a new building over a known active earthquake fault. Fine print said nothing about retrofitting the building, but the student-athlete building was a new building. So we brought in and trenched to look for the fault. And this was really exciting for the geotechnical engineers. I did not want to get down in that, but they went down and they mapped it. And when they could very clearly find where the fault was. What was important through this process was understanding where was the fault and where was it not. So we knew it's there. There were many times as a Cal football fan, I was hoping that the fault would just open up and the team would fall in. But then later on I decided I had this challenge. This had never been done before. No one had ever tried to do this. So we started to study. What did we know about fault rupture behavior? What we had been given is this fault will displace as much as 6 feet horizontally, 1 to 2 feet vertically. So here was San Fernando, an example of a vertical displacement. But notice that there's not a crack in the glass in the building. This building was not so lucky. This building had a sister building in the foreground that was destroyed. You can see the damage. The issue in this building was that it was a pile-supported building. And that began to tell us something, as well as this tree its trunk was severed. Imagine the roots that go down. And that's what engages the fault rupture, gets attracted into it by trying to strengthen the foundation. Here was a case of a little bunker-like building that basically just was so rigid and was on a little mat footing that all that happened when the rupture and displacement happened is it rotated, tilted a little bit. We decided that was a good life safety solution. So what we ended up with was this. In diagrammatic form, we were creating this fault rupture block, seismically separated, and seismically separated not just through the superstructure, but all the way through the foundation. That's usually not done. The block would be located on a very rigid, level, mat foundation, so that in the event of a rupturing earthquake in, whoops, I advanced it, in this zone right here, that all that will happen is that it will rotate or displace. So we ended up creating these two fault rupture blocks, one on the north, one on the south. Geotechnical engineers, seismologists gave us not only the probability of locations, but the angle of where they thought the rupture would occur. We went through a gazillion parametric studies of figuring out where could it occur, could it be multiple ruptures, sympathetic ruptures, but we ended up with putting one joint at the most likely location of the and angle of the fault rupture. We did an abacus finite element analysis of the building. Again, those are not columns, that was soils, I don't mean columns, but piles. We did not want to strengthen the soil, but we needed to densify it. But it's on a mat foundation and a very rigid structure. So I have a little animation here that is a little slow, but it will, the third, I like this Google Earth kind of focusing in. But it's going to 3 times go through, this we did use with the client to explain to them what we were doing. You won't see it on this one, we kind of animated a rupture through this, but you'll see a couple of other views. This is beginning to get better. You'll see the fault rupturing on the floor of the stadium. You'll see the block moving. This last animation is the best. But you see the rupture, the vertical rupture, horizontal rupture. You see what we, again, accentuated, but still it was important to the client to see that. What was interesting is everyone expected us to do some fancy sort of base isolation, and yet we did really, really basic stuff here. What we didn't use basic stuff for was the west wall. We thought, we spent all of our time on the fault rupture blocks because we thought, we know how to seismically strengthen a concrete structure. We were so wrong. So this is a section through the west wall of the stadium with a new press box. So you see one segment, but you see this triangulated structure, you see a concrete core on the right side, and this press box on top. What we found was when we first started saying we'll add some shear walls, and we're using the concrete cores to support the press box, but that triangulated, the raker beams of the stadium were creating a strut, and it kept failing on us, it kept buckling on us. So we said, okay, what we need to do is unbuckle it. We'll just put a slider at the base of the raker. But we were getting so much yielding at the top of the core, so we thought that's okay. We'll put some energy dissipation in the system. It's the first time I asked an architect to put an opening in a shear wall. Usually it's the other way around. And even then, we still found that we were getting a lot of yielding. So we finally said, why are we fighting it? Let's cut the core and the press box free and have them be seismically independent. We created a collar around it, a space, And that was pretty much the solution, but then we threw in hydraulic dampers around each of them to control the differential motion between them. We had a great time doing the analysis on this. We also did a nonlinear finite element analysis. And then this is another little animation. I mean, you can just see the core in the press box moving. I mean, actually the wedge bowl is moving, but just not as much. The press box was a huge structure. It was 250 feet long. Laterally spanned 240 feet. Here are a couple of, it's probably a little bit more reinforcing steel than you see in most shear walls of Utah. In the concrete pours, we use vertical post-tensioning. You'll see in this photo on the left side, you see these, in the light gray is the post-tensioning conduit, and then these are all number 18 rebar bars that are preventing the thrust of that. For scale, here's a construction person. On the left is the Revit model with the bowl slab turned off. Here's the stadium with 4 tower cranes under construction. Essentially, I said we retrofitted the building. We saved the historic perimeter wall and we demolished everything inside. What is this? This shows 23 concrete trucks on a large mat foundation 4 day. What is important about this is that every single piece of material and equipment had to come through that North Memorial Arch. This again was something we had to think about in the course of construction. This is, you see the west bowl being formed. You can see the concrete pours beginning to come up above. That's a joint in the upper right-hand corner is the joint in the between the fault rupture blocks. So this is the press box. This was fabricated in a shop, assembled in a shop, disassembled in the shop, brought on trucks into the stadium, reassembled on the floor of the stadium. Then they brought in that little yellow crane to put together the big crane that came in on 73 flatbed trucks. I don't think I have a picture. The day they put all the ballast on to counteract the picking weight of it, it blew out all of the tires because they had been stored in the Nevada desert for 3 years. So they FedExed something like 24 tires. I'm not sure I realized the size of the FedEx envelope for that. But then they picked up, they disassembled part of it and picked up the press box in 5 pieces. The way we designed the press box had a lot to do with the way it was all being delivered. Otherwise, because we designed it to be radial transverse truss elements rather than designing it. It took more erection time, but it was absolutely. These are a picture of the dampers, the finished stadium. I think we've won 3 games since the completion of the. It was interesting that the architectural concept for the press box was to not compete with the historic fabric. They wanted it to be this floating structure over the top, and in a way it works. You can see kind of the light below it. And my last slide is my last superimposed timeline. It shows my involvement in the Structural Engineers Association, my professional activities, EGRI, all of these things were really important to my career. And then at the very bottom, I'm at the point in my career where I get to do exactly what I want. And what I want to do is to be an advocate for safety. I'm very involved with Build Change that's doing seismically safe housing in the developing world. And I'm not sure without ERI and without the ability of these twists and turns my career made, I can tell you at the end of my career, I've loved every minute of my profession. And I highly recommend that this profession. It really is. It's very exciting. Keep your eyes and ears open, and I think you'll have a great time. That's it.
So for the San Francisco City Hall, you guys put in a base isolation system, effectively having your whole seismic loading on it. Why did you have this system at Dome?
Because there was still, remember this response spectrum and the period shift, there was still 0.2 G that could be experienced. And plus there were some other problems in the building. So besides just putting in elements, earthquake engineering in our lateral system, it's a connectivity that's important, and connections that are important. So there were certain things that still needed to do to stiffen those light ports, as well as deal with some of the load transfer. That was why we still have it.
What was the budget for the stadium retro?
The budget for the stadium retrofit was $123 million. That was the budget. We completed at $124 million. So we were pretty gratified by that. But that was, there were a lot of people who didn't want us to do it. They thought it was dangerous to do it. I honestly think today we know how we would design a building to straddle a fault. Not that we would do it, but I think we could. I have no reservations. Somebody asked me which building I would want to be in of the ones that I designed in my career. It would be San Francisco City Hall or Memorial Stadium. Maybe not the press box. The press box is going to be one wild ride. That's a very good question. I don't know if you could hear it. The question was, do you need to be able to replace the isolators? You need to be able to replace them, yes. The floor has access ports so that you can take them out and replace them. There is also now a code requirement that every 5 years you have to take out 2 or 3, ship them to Nevada to a testing rig, and make sure that they're still behaving the way they should. The worry with elastomeric bearings is that the rubber could have hardened over time. The material experts say it's not going to happen because of the nature of it. The worry about friction pendulums is we know that steel on steel over long periods of time can weld themselves together. So they also have to be tested as well. By the way, before they actually get inserted, they all go through a production testing, which is rather expensive. Today, I think the code required testing requirements are excessive. I think as the technology begins to prove itself a little bit more, some of that can be relaxed. Other questions?
What was the anticipated displacement for that press box on the California Stadium?
The fault rupture displacement? Oh, on the press box?
On that press box.
The lateral displacement, transverse lateral displacement of the press box is huge. So can you imagine kind of the whole thing is funded by the expensive seats, which are in little acres. imagine a $1 million donor that's going to feel like All right. Thank you for your time.
I just had the most